Hello and welcome to combinations of functions. We're going to talk today about two different types of ways that you manipulate functions. The first way has four parts, and then the second way is unique unto itself. The first thing we talk about are combinations, that being the sum, the difference, the product, and the quotient of functions. So let f and g be two functions with overlapping domains. Then for all x common to both domains, the sum and the difference, the product and the quotient of f and g are defined as follows. So if I were to sum them, I would add the two equations. If I were to subtract them, then, or take the difference, I would subtract them. Product, I would multiply them. Quotient, I would divide them. These are going to be just some very basic operations, hopefully not too challenging, mostly in with combining like terms. So for example, finding the sum of two functions. Given that f of x equals 2x plus 1 and g of x is x squared plus 2x minus 1, find the sum of f and g of x. Then evaluate the sum when x equals 3. Now, if I were to tell you to find the sum of 3 and 7, you would just add them, right? That's all you're having to do here. So, if I add them, then I basically have the first one here, 2x plus 1. The second one here, x squared plus 2x minus 1. All I'm doing is I'm adding the two functions. So by adding the two functions, I just combine like terms. This is the easiest of the operations. So x squared doesn't have any like terms, it becomes x squared. 2x plus 2x is 4x. Positive 1 minus 1 is 0. So now to evaluate the sum of it, I just plug 3 in for x in that equation, and I get 3 squared plus 12, which is 21. So all I did here was combine the two by combining like terms. In the second one, the difference of two quotients, I have the exact same functions. Now find the difference. Then evaluate at x equals 2. Now, the key thing that I always see students make a mistake here on, is this minus. This minus gets distributed to this entire equation, which means it's going to flip the signs on everything. Instead of x squared, it'll be negative x squared. Instead of positive 2x, it'll be minus 2x. Instead of negative 1, it'll be positive 1. So I'm going to have negative x squared, there's nothing with it. 2x minus 2x is 0x. So that's eliminated, and 1 plus 1 is 2. So now I plug in negative 2 in that equation, or I plug in 2 in that equation because it says to evaluate when x equals 2, and I get negative 2 squared plus 2. Another key mistake that I see young people making is dealing with this negative right here. This negative right here that's on the front, because it is not inside the parentheses, I cannot square it. The negative remains. Always remember your order of operations. Use them or lose points. Now over here we're going to talk about the product of two functions. So let's say I've got x squared and x minus 3. Find the product of f of g of x, and then evaluate the product when x equals 4. To multiply them together, I just simply multiply them together, like you can see here. In this case, it's a very simple operation. Distribute the x squared through, and I get x cubed minus 3x squared. This is not any different math than you have ever done before. It is simply stating it differently than you've done it before. So now I plug in 4. 4 cubed is 64 minus 3 times 4 squared, which is 3 times 16, which is 48. 64 minus 48 is 16. The quotient you have to divide. Now this is where it gets more complicated because people don't like making fractions. The number one complaint I always hear from students is that, oh, it's a fraction. I hate fractions so much. That's all I hear all day long, trust me. So find the quotient of f of g of x and the quotient of g of f of x with these functions. So the quotient simply is the square root of x over the square root of 4 minus x squared. And the quotient of g and f is the opposite, square root of 4 minus x squared and over the square root of x. I can't do anything more with that. That's all I can do. I can do no more. Now, it asks me to find the domain and the range, or find the domain of each. So I look at these equations to find my domain, and my domain is going to be, in this case, a restricted domain. Notice the domain of the first function is between 0 and 2. The domain of the first function is between 0 and 2, but notice that it includes 0 but does not include 2. The bracket means it includes it, the parentheses means it does not. It goes up to it almost all the way and then it stops. Whereas the opposite is true for the other equation. The reason for this is that the domain of the original equation, f, is from 0 to positive infinity. However, the domain of g is from negative 2 to positive 2. Because the only way that you can do that, anything more, and it goes outside of what you can do with the radical. Remember, you are considering the equation the square root of 4 minus x squared. So if I go beyond negative 2 to negative 3, then I have a negative radical and it no longer becomes a real number. Because if I plug a negative 3 into this equation and I square it, either a 3 or a negative 3, I get 9. 4 minus 9 is negative 5. I cannot take the square root of a negative number and have a real answer. We're not dealing with imaginaries here. So as a result, I have to restrict my domain. My domain for that equation was restricted at negative 2, comma 2, which means that I have to restrict my domain for the bottom one as well, or for the combination of the two functions by the quotient. By doing so, it restricts the domains to including 0 but up to 2, and up almost to 0 and including 2. Now, a composition of functions is a different beast all of itself. A composition of two functions is where, I'll read you the definition, the domain of f of g, the composition of f and g, is the set of all x in the domain of g such that g of x is in the domain of f. The composition of two functions, to do that, I simply put an equation into another equation. So in the first equation, I've got x plus 2. F of x equals x plus 2, and g of x is 4 minus x squared. So find the composition of f with g, the composition of g with f, and then evaluate g with f at negative 2. So because I have the composition of f with g in the first one, I'm plugging g into f. So everywhere I have an x in the f of x equation, I just simply plug in the equation of g. So instead of f of x equals x plus 2, I now take 4 minus x squared and plug it into that equation. You can see that demonstrated right here. So notice this is basically x plus 2, but now I'm plugging in 4 minus x squared in for that. So now when I plug that in, I just simply combine like terms, and the composition of f with g is negative x squared plus 6. The composition of g with f then becomes, instead of plugging in 4 minus x squared, I plug in x plus 2. So now I have 4 minus x plus 2 squared. So I have to expand x plus 2 squared to get x squared plus 4x plus 4. Now notice I have a negative here. That negative has to be applied to the entire equation. If I don't apply that negative to the entire equation, then I have done it incorrectly. So now I'm going to have negative x squared minus 4x minus 4. The 4 and minus 4 cancel out, so I have negative x squared minus 4x. Now, if I were to evaluate negative x squared minus 4x for negative 2, I can plug in negative 2 in the equation, square it, but I still have that magic negative on the outside. Don't forget that it's on the outside, it's different. Here's a key example of where you have one on the inside and the outside. Negative 2 squared is 4, but times negative 1 is negative 4. And then negative 4 times negative 2 is positive 8, so then the answer is 4. So, combinations of functions, we're adding them, we're subtracting them, we're multiplying them, we're dividing them. Combinations or compositions of functions, we put one function and plug it in for the variable of another function, like we did here with x plus 2 in for x in the equation 4 minus x squared.